All right, picture this. An aircraft, right? But it doesn't need like miles of runway. It can operate from a tiny clearing, a ship's deck. It just goes straight up.
Wow.
Sounds a bit sci-fi, doesn't it?
Yeah, it does.
But that's VSTOL, vertical short takeoff and landing aircraft.
Right.
And for everyone with us today, we're diving deep into the story behind this capability.
And it's a longer story than people think, and more inventive.
Definitely.
It's amazing, really, from an engineering standpoint. You're essentially taking this massive, heavy machine and making it defy gravity.
Exactly.
But getting rid of the need for traditional runways, well, that unlocks a lot of advantages, especially for the military. Think about it deploying and concealing aircraft without relying on these fixed airfields, which are super vulnerable.
Makes them way harder to target. And on this deep dive, we're taking you through the whole evolution. We'll start with some early, kind of surprising attempts by Germany back in World War II, then move through all these Cold War prototypes, a lot of really creative, out there ideas.
Oh, yeah.
And then bring it right up to the modern aircraft we see in action today. Yeah. It's a real showcase of how ingenious people can be when it comes to solving problems. Though, I gotta say, some of these early designs, well, they're kind of head-scratchers.
They definitely were.
But making something fly straight up, that comes with some engineering challenges.
They're huge challenges. I mean, you always have this trade-off between vertical lift and the aircraft's overall performance, like how much it can carry weapons, payload. That was a major limitation, especially early on, because of the power needed just for vertical ascent.
Yeah, just getting off the ground takes a lot of oomph.
Oh.
And it's not just about the initial liftoff either.
No.
Developing these machines, maintaining them, that's expensive.
Oh, hugely.
I mean, just look at the F-35B program today and all the debate around its cost.
Exactly.
And then you've got the pilots. Can you imagine trying to land one of these things vertically in the early days?
I can't even imagine. It's a wonder they managed at all.
I know, right? Even with modern simulators and all the digital flight controls, it's still incredibly demanding. It takes a huge amount of skill to pilot these things.
Oh, absolutely. So what we're aiming to do in this deep dive is kind of unpack all of that, right? We'll hit the most important milestones and give you the key takeaways without getting too bogged down in the technical stuff. So think of this as your guide to understanding VSTOL.
Your shortcut to becoming a VSTOL expert.
Exactly. So let's start with those early German experiments, shall we?
Let's do it. Now, World War II Germany, not the first place that comes to mind for positive, long-lasting impacts. But they were experimenting with some pretty futuristic ideas in aviation.
They were. Definitely ahead of their time in some way.
And some of it was, well, pretty bizarre. One of the earliest attempts at a vertical launch system was the Messerschmitt Me 163 Comet, nicknamed Viper.
The Comet.
This was a rocket-powered interceptor. Its whole purpose was to get into the air quickly and attack Allied bombers.
Yeah, it was all about speed and hitting hard and fast.
Right. And the sheer force they used for its vertical launch. I mean, it had this liquid fuel rocket engine producing 1,700 kilograms of thrust for about 70 seconds at full power.
That's a lot of power.
And then, to get it off the ground, it used 4, get this, jettisonable solid rocket boosters, each one giving 10,000 kilograms of thrust, but only for about 10 seconds. It was all about a super quick burst of power.
Yeah, just blasted up there.
It's a good example of the early challenges with this whole concept. You need enough upward force to get this thing off the ground vertically, but you can't sacrifice control or payload. And that's a balancing act that has defined VSTOL development, really, ever since.
For sure. And the Comet, it wasn't exactly a success story, was it?
No, not really. It was fast, but the limited flight time and how hard it was to handle, well, it never really became a big threat.
Right.
But it definitely got people thinking about vertical launch in a new way. And then there are these other German designs. Some of them never even got past the drawing board, but they were wild. What about the Focke-Wulf Triebflügel?
Oh, the Triebflügel. Now that was a unique idea. Instead of regular wings, it had these 3 rotating blades around the body.
Rotating blades.
Yeah, and each blade had a jet engine at the tip. The whole thing would spin like a helicopter rotor to create lift. It was supposed to be a short-range interceptor. You really got to see the drawings to get it.
A spinning airplane, hard to wrap your head around.
Right. Talk about thinking outside the box. But you can see how wartime pressures lead to these unconventional ideas.
Absolutely. And then there's the Heinkel Lurch. This one sounds equally strange, but in a different way.
The Lurch, yeah, that means lark in German. It had a circular wing, literally a circle, going all the way around the fuselage. Hmm. And they planned to use propellers both at the front and the back for thrust. Again, this was a design for an interceptor never actually built, but it shows just how many different approaches they were exploring.
So many different paths.
Hmm.
But what's interesting is that even the failures,
Right.
they helped define the problem. They inspired future solutions, even if they didn't work themselves.
Exactly. Knowing what doesn't work is just as important as knowing what does.
Okay, so fast forward to after the war. The U.S. Navy starts getting interested in operating aircraft from smaller ships.
Yeah.
So naturally, they start looking at propeller-based designs for that vertical lift.
They did. They were going for, I guess you could say, a more traditional approach, focusing on propellers to get that lift.
Mhm.
Two key examples were the XFY-1 Pogo and the XF-2Y-1 Salmon.
The Pogo. Even the name sounds kind of bouncy.
Right. Both of these aircraft used contra-rotating propellers.
Contra-rotating.
So two propellers, same axis, spinning in opposite directions.
Ah, okay.
This helps to cancel out the torque, makes the aircraft more stable.
Makes sense.
And both the Pogo and the Salmon actually had successful test flights.
Oh, really? So the basic concept worked.
It did, yeah. They proved that you could get vertical lift from a smaller platform using propellers. But the big challenge was landing.
I can imagine.
Think about trying to control this thing that's basically hanging vertically by its propellers, then slowly bringing it down to land, tail first, on a small platform.
Oh, man.
It was really difficult and dangerous for the pilots.
Yeah.
And that's why they eventually abandoned both projects. It was just too unstable, too much for the pilots to handle during those landings. And it shows that getting up is just the first step. You got to be able to come down safely, too.
Makes sense. So now we move into the jet age, and there's this push to find new ways to get that vertical lift moving beyond propellers.
Absolutely. Jet engines opened up a whole new set of possibilities.
And a good example of this shift is the Ryan X-13 Vertijet. Now, this was a jet-powered aircraft, and its landing method was, well, let's just say unique.
Yeah, unique is one way to put it. Instead of landing gear in a normal runway approach, they used a hook on the nose of the aircraft.
A hook?
Yeah, to catch a wire strung across a tower.
So basically like a stunt plane at an air show.
Pretty much. It had a delta wing, about 6.4-meter wingspan, and it did manage to take off and land vertically using this system, but with the speed and range of a fixed-wing aircraft.
It's an idea that's central to a lot of modern VSTOL designs, isn't it?
Absolutely foundational.
So how well did the XB3 actually do in demonstrating this transition?
It did pretty well, considering the technology at the time. The XV3 actually successfully transitioned between those two modes 110 times between December 58 and July 62.
Wow, that's impressive.
It was. It proved that this tiltrotor concept, it wasn't just a pipe dream, it could actually work. Of course, it took many years of development to make it practical and high-performing,
Right.
but the XV3 was that crucial first step.
It showed what was possible. And then there was the Ferry Rotodyne. This one was from the UK, and it was another kind of hybrid approach, right?
Yeah, the Rotodyne was interesting. It wasn't a pure jet VSTOL, but it definitely contributed to the evolution. It used a big rotor for vertical lift, like a helicopter. But then for forward flight, it would switch to fixed wing mode. The rotor was still there, but it wasn't providing the main thrust anymore. It was more like a lifting surface.
So kind of a blend of both. They were hoping to use it for both civilian and military transport, right?
They were. It had a lot of promise, offering vertical takeoff and landing with good speed and range.
What happened? Why was it canceled?
A couple of reasons. One was the noise. Those rotor tips were really loud, and that's a problem if you want to use it near cities or for civilian applications. And then there was the funding. The government support was inconsistent, and ultimately, they just didn't get enough of it.
Ah, funding issues. The death of many promising project.
It is. So despite its clever design, the Rotodyne never really took off. And this shows how, even with great technology, external factors can kill a project.
It's not always about the engineering.
Yeah.
Okay, so now we're fully into the jet age for VSTOL, where the jet engines themselves are used for vertical lift. The Bell X-14 was an important early experiment in this area.
It was. The X-14 was all about exploring vectored thrust, basically redirecting the engine exhaust to control the aircraft's direction, including upwards for vertical takeoff.
So pointing the exhaust where you need the thrust.
Exactly. It wasn't meant to be a combat aircraft, but it was a crucial test bed for the control systems and all the tricky aspects of jet-powered VSTOL flight.
It was about figuring out the basics, really.
Yeah, and the X-14 contributed a lot to later aircraft, like the Harrier and the F-35. Its legacy is in the knowledge it generated about how to control jet-powered vertical flight.
A stepping stone. And around the same time, the British were making progress with the short SC.1. This was their first jet with dedicated jet propulsion for vertical lift, right?
It was. The SC.1 was a real pioneer. It used 5 Rolls-Royce RB108 Jeb engines. 4 of them were mounted vertically in the fuselage, just for vertical lift. The 5th one was in the back for normal horizontal flight.
So dedicated system for going straight up.
Exactly. And what's really interesting about the SC.1 is that it was one of the first to use automatic flight control systems.
To help manage all that complexity.
Yeah, because VSTOL flight is inherently complex. So even though it never went to production, the SC.1 made big contributions to the flight control techniques that were later used in the Harrier.
Another important stepping stone.
Okay.
And that brings us to the icon, the one everyone knows, the Harrier.
The Harrier.
It all started with the Hawker P1127, the prototype, and this was the first aircraft that really nailed operational VSTOL capability.
It was a game changer for sure.
Hmm.
The P1127 showed that a jet could not only take off and land vertically, but could also be a real combat aircraft.
Right.
And its successor, the Kestrel, was even better. It was a transitional version that led directly to the Harrier we all know. These 2 programs really proved that jet VSTOL was viable for military operations.
And the Harrier, especially the Sea Harrier variant, really proved its worth in actual conflicts.
Absolutely. The Harrier was revolutionary. It used the Rolls-Royce Pegasus engine. This engine could swivel its nozzles, down for vertical lift, back for normal flight.
Vectored thrust.
Exactly. And the Harrier was used by the Royal Navy, U.S. Marine Corps, and other air forces around the world. It really showed its value in conflicts like the Falklands War.
Right.
Being able to operate from small carriers, forward bases, places where you couldn't have a normal runway, it was crucial. And the Sea Harrier, well, that was specifically designed for naval operations. It excelled in air-to-air combat and defending the fleet. A real testament to how flexible VSTOL could be.
So the Harrier showed everyone what was possible. But the Cold War was a time of intense innovation, especially in aviation. And there were a lot of other VSTOL experiments going on, some more successful than others.
Oh, yeah, tons of them. Some pretty wild ideas in there.
Let's talk about some of these less famous attempts.
All right, so you had the French Esnecmes C.450 Coleoptère. This thing looked bizarre. It had an annular wing, meaning the wing was a complete circle around the fuselage.
Like a big flying donut.
Kinda, yeah. More like a dart, maybe.
Hmm.
It was supposed to take off and land vertically, but controlling it, especially transitioning to horizontal flight, was incredibly difficult.
Yeah, I bet.
And unsurprisingly, it crashed during testing, and that was the end of that. It shows how tricky it can be to control these unconventional designs.
A circular winged aircraft that crashes. You really got to see the pictures to believe it. What other unusual approaches were there?
Well, there was the Hiller X-18. It was meant to be a cargo transport, and it used tilt wing technology.
So the whole wing tilted.
The whole thing! It had 2 turboprop engines with contra-rotating propellers.
Yeah.
And then there was Lockheed's attempt, the XH-51A compound. It was also called the Jet Lift, or the XB-4A Hummingbird.
Okay.
This one used ducted fans built right into the fuselage for vertical lift.
Ducted fans.
Yeah, basically fans inside a duct or shroud.
Ah, okay.
But its performance wasn't great, and they ended the project after an accident.
Another good example of how things don't always go to plan. And those ducted fans, we see them again in later designs, don't we?
We do, yeah. Interesting how ideas come back around.
What about France? They had another go after that. What was it called?
The Coleoptère.
Yeah, after the Coleoptère.
Right. Well, they had the Dassault Balzac. It was actually based on their Mirage, the third fighter, which was really successful.
So they were trying to adapt an existing design.
Yeah, they were. The Balzac used a mix of lift engines, just for going up, and a separate engine for normal flight.
So 2 separate systems.
Exactly. But the program was plagued with accidents, including a fatal one, and they eventually canceled it. It's another example of how this technology can be dangerous to develop.
Yeah, for sure. It's high risk.
It is.
Yeah.
They also had this modified Mirage, the third they used as a testbed. They put 8 Rolls-Royce RB108 lift engines in it, all vertically mounted in the fuselage.
8. Wow.
Can you imagine the amount of thrust that thing must have had?
Must have been incredible.
It shows how committed they were to figuring out VSTOL.
Now, Germany also had a pretty ambitious project, the VJ-101. A supersonic VSTOL fighter.
Oh, yeah, the VJ-101. That was a bold project for the time.
It was. It used 6 vectored thrust engines, 2 on the wingtips that could swivel, and 4 more mounted vertically in the fuselage. And get this, it actually achieved supersonic flight while taking off and landing vertically.
Wow, that's impressive.
I know, right? But again, it came down to cost and complexity. It was just too expensive and too complicated to make it practical.
Yeah, that's often the challenge with cutting-edge technology, balancing the capability with the practicality and cost.
And it was the 60s. They were really pushing the limits.
And-
What about the U.S.? Were there any other notable VSTOL experiments going on during this time?
Oh, plenty. You had the Curtiss-Wright X-19, which was a tilt-rotor transport aircraft. Interesting footnote. It was the last aircraft Curtiss-Wright ever built.
The end of an era.
Then there was the Ling-Temco Vought XC-142, another experimental tilt-wing transport. That actually worked pretty well, could transition between vertical and horizontal flight.
So why didn't it go anywhere?
Lack of interest. The military just wasn't that keen on it.
So another promising concept that just didn't get the support it needed.
Right. And Canada had the Canadair CL-84 Dynavert, another tilt-wing design. They only built 4, and 2 of them crashed due to mechanical failures. It highlights how tough it was to make this tilt-wing concept truly reliable.
It was a high-risk, high-reward kind of technology, a lot of potential, but a lot that could go wrong, too. Now, what about the Soviet Union? They weren't just sitting back watching all this happen.
No, they weren't. The Soviets were definitely in the VSTOL game. Their first real VSTOL aircraft was the Yakovlev Yak-36. It had 2 turbojet engines side by side in the back with nozzles that could rotate, kind of like the Harrier.
So they were exploring similar ideas.
They were. Then came the Yak-38. This one actually saw more widespread use, operating from those Soviet aircraft carriers, the Kiev class.
Okay.
But compared to the Harrier, the Yak-38 wasn't as good in combat, and its safety record. Well, let's just say it wasn't great. Lots of accidents.
It seems like the Soviets struggled more with mastering this technology than some Western nations.
It does seem that way. And a high accident rate? Well, that's a reminder of just how complex and risky these aircraft can be.
Right. Now, there was another concept that always stood out to me, the Ryan XB-5 Vertifin.
Oh, yeah, the Vertifin. That was a cool idea. It used fans built right into the wings and fuselage to create that vertical thrust.
Really integrated design.
It was. The idea was that by doing it that way, you would reduce drag during normal flight.
Makes sense.
But the system was really complex mechanically, and they had a few accidents during testing.
So they scrapped it.
They did. Too risky. It shows that sometimes a really innovative idea on paper, well, it's just too hard to make it work reliably in the real world.
You got to balance innovation with safety and practicality. Okay, let's move closer to the present day. We start seeing the tilt-rotor concept making a comeback, becoming a truly viable option with the Bell XC-15.
Yeah, the XV-15 was a big moment for tilt rotors. It was the second experimental convertiplane that Bell made, and it was the first to really show that this technology was more than just a theory.
So it was much more refined than that earlier XV-3.
Oh, much more. It addressed a lot of the limitations and paved the way for the V-22 Osprey. They only built 2 XC-15 prototypes, but they did a ton of flight testing.
To really put it through its paces.
Exactly, and it worked. It proved that you could have the vertical lift of a helicopter and the speed and range of a turboprop aircraft, all in one.
The best of both worlds. And that leads us to the modern era of VSTOL, where we see the evolution of the Harrier into the AV-8B Harrier II, a joint US-UK project that really improved the original design.
Yeah, the Harrier II shows that the original Harrier concept, it really had legs. It was developed by McDonnell Douglas in the US and British Aerospace in the UK.
A true collaboration.
It was. And the Harrier II had a lot of improvements. Better aerodynamics thanks to those composite wings, more advanced avionics, and it could carry a lot more, both weapons and payload.
A much more capable aircraft.
Definitely. And it's been used extensively by the U.S. Marine Corps, Spain, Italy, and of course the British Aerospace Sea Harrier FA-2 was used by the RAF and the Royal Navy. They all showed how effective VSTOL could be in different roles.
So a real success story. And while all this was happening with the Harrier, the Soviets made one final push for a really advanced VSTOL fighter, the Yakovlev Yak-141. It never entered full production because, well, the Soviet Union collapsed.
Right.
But it had some really innovative features.
It did. The Yak-141 was the peak of Soviet VSTOL development. It had a few cool things going for it. It had a dedicated lift engine in the front, in addition to the main vectored thrust engines in the back.
So 2 separate systems for lift.
Yeah, and that was supposed to improve its vertical takeoff and landing performance and make it more agile overall. They were also aiming for supersonic flight in level cruise, which would have been a huge deal for a VSTOL fighter.
Pushing the boundaries.
And the Yak-141 used a lift fan concept that's similar to what we see in the F-35B. It suggests that designers in different parts of the world were arriving at similar solutions independently.
It's fascinating how that happens.
It is, and it's a shame the AC-141 never really got a chance. It could have pushed VSTOL technology even further.
Now, let's talk about a VSTOL aircraft that's in widespread use today.
Hmm.
The Bell-Boeing V-22 Osprey.
Ah, the Osprey, a truly remarkable aircraft.
It's really blurred the lines between helicopters and airplanes. It can take off and land vertically, but it has the speed and range of a turboprop airplane. It's been invaluable for the U.S. Air Force, the Marine Corps, and even Japan.
It's a testament to how far tiltrotor technology has come. It can do things that neither a helicopter nor a regular airplane can do on their own.
And of course, there was the Joint Strike Fighter competition, which led to the F-35. Boeing had the X-32 with its direct lift fan,
Right.
but Lockheed Martin's X-35 won out, and that became the F-35. It's interesting that only one of the X-35 prototypes actually had VSTOL capability.
It is. Both companies were trying to meet the requirements, which included a STOVL capability for certain versions.
Short takeoff and vertical landing.
Right. Boeing's X-32 used a direct lift fan in the front. But Lockheed went with a more complex lift fan system for their F-35B, and that proved to be more effective.
So different approaches to the same problem.
Exactly. And it shows the kinds of trade-offs engineers have to make when designing for VSTOL, especially in a stealth fighter like the F-35.
It's a whole other level of complexity.
Hmm.
And speaking of the F-35B, well, that's what many consider the pinnacle of modern VSTOL technology, right?
It's up there, for sure. It's designed to replace the Harrier, and it's being used by air forces all over the world.
A global aircraft.
It is. It combines stealth, advanced sensors, and VSTOL capability all in one. And unlike the Harrier, which used those swiveling nozzles on the Pegasus engine,
Right.
the F-35B uses a lift fan system developed by Rolls-Royce.
A dedicated lift system.
Exactly. It's a kind of similar in concept to the lift fan the Soviets were planning for the AC-141. It's basically a fan in the front, powered by the main engine, that provides the main vertical thrust, and then there's a swiveling nozzle at the back for additional control.
So a much more integrated and sophisticated system.
Oh, yeah. It's a really powerful system that lets the F-35B be stealthy and still take off and land vertically. It's a remarkable aircraft, a truly unique capability.
So it's been quite a journey, hasn't it?
It has.
From those early rocket launches to these incredibly advanced aircraft today. What do you think the future holds for VSTOL technology?
I think it's looking really exciting. We're already seeing AI being integrated to help pilots during takeoff and landing.
Yeah, to make it easier and safer.
Exactly. Less workload, fewer accidents. And we're also seeing a lot of progress with engine design and lighter materials.
So what does that mean for future VSTOL aircraft?
Well, they could carry more, fly further, and be more fuel efficient. It could even revolutionize commercial aviation. Imagine flying directly from city centers, no need for huge airports.
So maybe not flying cars exactly, but a different kind of urban air mobility.
Yeah, exactly. And beyond traditional aircraft, VSTOL is also huge for drones.
Unmanned aerial vehicles, UAVs.
Right. VSTOL drones are great for reconnaissance, transport, even combat, especially in remote or dangerous areas. In a future where speed and flexibility are crucial, well, VSTOL is going to be a key technology.
It allows operations in places and under conditions that were just impossible before. It's a real game changer.
It is, and the whole development of VSTOL, from those early kind of basic ideas to the sophisticated aircraft today, it shows how innovative and persistent people can be. There's been challenges, but the solutions have been incredible.
And this technology, it's not just about military power. It could change how we travel, how we transport goods. So many possibilities.
Absolutely.
So here's a final thought for you.
Given all we've talked about, what other applications, what breakthroughs might VSTOL enable in the future? Not just the obvious military and commercial uses. Think bigger. How could it impact things like urban planning, emergency services, even personal air travel on a scale we haven't even imagined yet?
A lot to think about there. Some really fascinating possibilities. Well, thank you for joining us for this deep dive into the world of VSTOL aircraft. It's been an amazing journey.